Finally, we can present a graphical solution if we define our equations like these. We're going to solve for y from both, and then define a couple of variables, a couple of functions of x. f1, which is going to be equal to 6 minus x, and f2 equals 5x minus 12 over 4, which are the values of y obtained from here. Then we're going to recall back to one of the previous videos when we did a graphic, and you're probably able to figure out all the terms in here. And when you get there, is that the red line is the first equation, and the green line is the second equation, and the intersection is the solution. In this case, of course, we go for some simple solution for 2 for x and y, and that would be a graphical solution. But the graphical solution are not too reliable, because if it is not a nice integer system like this, then it's going to be more difficult to figure out. If we don't want to isolate the y's, we can use an implicit reference to the equations with indicating the values in which we want to plot x and y. And in this case, we get the same result, or the same graphic actually, but done in a different manner. We could have a system of equations that represents the same curve. This equation right here is the same as this one, but multiplied by 3. If we try to solve that, we get that y will be referred to a variable, an arbitrary variable, percentage R1, and for every value of y, you can have a value of x. So every point in the line is a solution, and this is what this is telling us. We can try to solve implicitly the two equations, and what we get is a single graph, because the two lines are exactly the same. If you have two parallel lines, you're going to have, for example, the coefficients here, or the x and y terms, are the same, they multiply by 2, but this is not 12 multiplied by 2. So what you have is two parallel equations that we're going to indicate here. If we say solve equation 1 and equation 2, we get an empty result indicating there's no solution. And if we plot those things, you get two parallel lines, and so they never have a solution. In summary, we present the 6 methods for solving a system of two equations, and we show you how to use the solve equation, or the solve command to solve equations. You can use it to solve almost any equation. If you have a cubic equation where we have 3 results, a fourth order equation, 4 results, a system, a linear system, that's first order equation with 4 equations, EQ1, EQ2, EQ3, EQ4. You can solve them, and then you get those results. System of 2 linear equations. This is a wrong entry right here. We can solve it like that. Oh, non-linear equation, sorry. So there's a whole lot of different combination of solutions that you can get. There is another command called linsolve, where if you define your functions or your equations like these, for example, you can just type linsolve, the list of equations and the variables. It's similar to solve, but it's specific for linear sum. And in the indeterminate system of equations will be ones where one of the variables is not fixed, and so there's not a single solution, just like we did with the case of the two lines that were the same line basically. For example, one of the equations repeated again, we get the same idea. Geometrical representation of 3 linear equations. These are planes in space. This is advanced algebra or advanced analytic geometry actually, but we can plot this to show you here. It's not really same for elementary algebra, but you have like the red plane is one of the first order equations, the blue plane is another one, and the green plane is another one, and they intersect at this dark point in the middle, and that's the geometric interpretation of a system of 3 linear equations. And so with that, we finished this video about system of first order linear equations.